So, good evening, all of you. I'm Ashish Bajpayee from IIT Kanpur, and this is the Week 10 NPTEL live session for computational fluid dynamics and heat transfer. And today I'm going to take up the Mac and simple algorithm and the code for a previous code for a Lytton cavity with the artificial compressibility method. And later we will take the Lytton cavity with simple algorithm as well as the turbulence lecture, whatever people wanted to ask some questions about turbulence, so we will take that. I'm waiting for some more people to come and then I will start. So let me start. Uh, I'll start with very basic of why we are doing this, and so we are doing it for getting the pressure. So pressure, we are writing. I am writing two equation, which is momentum equations. So del over del x. This is the advection term at n plus 1 1th time step, which is equal to viscous term. So from here we will get del square p by del x square and del square p by del y square. These terms. Let's add these two terms only. So this will be like t square t p over dx square del square p over del y square is equal to sum all the terms which we are content as source term, and this is what we call as Poisson's equation. And this is how we will get the Poisson's equations from these two momentum equations. So the thing is here why we are doing it. So because I am writing also pressure is not varying with time. In any of the equation, pressure is not varying with time. In the equation, this is the reason this causes difficulty to know the variation. This is the source term. All the terms are dumped into it. And so, Apur, this time any doubt? No, I am discussing about marker and cell algorithm, as some people asked in the last class. And one more thing, like having any doubt in the art assignments and other things. Okay, you are not able to submit it. Okay, because I haven't seen your assignments particularly. Although I must say that people are submitting, some people are submitting, but I have not seen a single copy who is submitting correct solution. And some people, if they are watching this lecture later, they are submitting it like they are mostly from one college, AMU college, and they are cheating. They are copying each other's copy, and there were 8 copies to whom I gave 0 marks because of cheating. It was complete cheating. So most of the assignments, like in last 2 assignments which I just checked was just copy paste. So if they are listening, they should not do it from the next time. Although I have given them remarks and I have given the 0 numbers to them. And you should also submit whatever you are getting in that. At least you will get some marks. This way you will not get any marks. So now so that is what I am going to take. Okay, like I tried to make it in a simplified form. That is why I am taking it. So later maybe you will not get any doubt in my algorithm. So our momentum equation is like du by dt. I am writing in one dimension only. Then advection term. I am not writing all the terms here. I will write this u du by dx u del u as advection term at the nth time step. Okay, and my del p by del x plus viscous term. I will also not write my viscous term here because it is difficult to write again and again. It is more easy to understand this. So this is what we call as our momentum equation in x direction. So in suppose first equation in A, we are discretizing it. Okay, so this will be uij minus uij, but at n plus 1th point, because we are moving forward, we are doing forward difference in time. So forward difference in time means this, and you can ask in any of the step which you miss. So this is equal to p ij at n plus 1th time step minus p I plus 1j, because it's a negative sign, so I am also doing forward difference in the space here, so which is also n plus 1th step. Because we don't know the pressure at next point, we can't predict it, so that is why I am writing for n plus 1th step and divided by delta plus all the terms, this term and this term, and this we can neglect also. So all the terms I am putting in residual. I am calling it residual at nth time step. So we are not writing any term, exact term here. Okay, and next what will I do? I will write at nth time step. So or the suppose I predicted some pressure value, and from that pressure value there will be some incorrect velocity term. So this is the correct velocity term from the next time steps pressure terms for the next time step velocity, but for some predicted values I am writing one equation. So after equation you will understand. So what I am calling is, let me write it here, B equation. So uij at nth plus 1th time step, which is predicted, this tilde means predicted value, minus uij, and we know the value of u at nth time step. Suppose we have 1 2, t is equal to 1, t is equal to 2. So t is equal to 1, we know the value of velocity, but we don't know the value of pressure at t is equal to 1 or 2. So that is what I am writing. This is we don't know, and this will be predicted by the pressure. The pressure is Pij at nth time step and Pi plus 1j at nth. So from the nth time step pressure value, we are predicting velocity value of n plus 1th time step. For the next time step I am predicting. And here, yeah, because this is the one which we require. This is the correct value, actually correct value of velocity, and this is at the next time step which we don't know. This values we don't know. These values we don't know. I am just writing it in an equation. These are unknowns. But suppose at boundary conditions, so yeah, it's yeah. 1 second. Yeah, it's a crest value. So this is t is equal to 1 at t is equal to 1, and this is t is equal to 2. Okay, at t is equal to 1, suppose you know the pressure value, okay, which is calculated, or suppose the boundary condition is given at p is equal to 0, something is given, you know the pressure value here, so you know the velocity value here, and for the next time step you want to find pressure, okay, but you don't know the pressure value there or velocity value there, anything you don't know. What you will do, you will predict the velocity value here from the pressure value here. So that is what I am doing. From the pressure value here, I am predicting a velocity value, which is a predicted velocity value. Okay, this is the first step. And later you will understand why I am doing. But this one should understand that this is the predicted value from the previous pressures. Okay. Let's add these two equations, or subtract these two equations. When we subtract, what will happen? A minus V Uij at n plus 1 minus U tilde ij at n plus 1. This value will come and divide by delta t. It is clear? And next, this Pij. So there will be two values, Pij and n plus 1 minus Pij at n minus Pi plus 1 j at n plus 1th minus Pi plus 1 j at n. Am I correct? Divide by delta x, and these residual term will go out. Okay. Then next is the same term, Uij at n plus 1 minus U tilde n plus 1 ij is equal to delta t by delta x. And suppose we call it as this Pij at n plus 1 minus Pij at n. I am calling this as P dash ij. Is it fine? So let's call it P dash ij minus P dash I plus 1 j divided by delta. Okay, not dividing. Okay, this one only. And let's call this. Okay. Okay, this much is clear. You can turn off your mic and mute yourself. Purv, you can mute yourself. So our target is, what is our target? Our target is to make this P dash as 0. Means this, when the P at n plus 1 and P at n will become equal, then we can call that we have reached the convergence. Okay, so this is our target. And so correction of velocity will become, this U tilde will become as U, and then we can say that we converged and we know the solution. We know the pressure field, we know the velocity field. Okay, and you can say the error, if you calculate P dash, it will become 0. P dash should become 0. When it is 0, then the error will be in the order of 10 to the power minus 7 to minus 10, and this very small value of error will signify that we reached our convergence. So let us apply at different points this equation at different point. So this our equation, let me write it here again. Copy, do not copy, let's write it. Okay, so for uij I'm writing, so for uij at n plus 1 is equal to uij tilde n plus 1 plus delta t by delta x p dash ij minus p dash I plus 1 j. This we have done. Let us do it for a step in the previous step in the backward phase, you can say up for a backward point or backward difference method by applying that. So just putting I as I minus 1, I can do it. So let's put it I as I minus 1 comma j plus n plus 1. So why I'm doing it? Because I want to satisfy this with a continuity equation. So this is our next step. I minus 1 comma j at n plus 1 plus delta t by delta x, and this is p dash I minus 1 comma j minus p dash I comma j. This is our next equation. Third equation, when we apply this to the v in the vertical direction, this vij at n plus 1 will become v tilde I j at n plus 1 plus delta t by delta x. One thing will change. This I will become, or I will not move forward. Here we will move forward in the j direction. So this p dash I comma j minus p dash I comma j plus 1, and then v I minus 1, and v j I j minus 1 n plus 1, and v tilde I j minus 1 n plus 1 plus delta t by delta x p dash I minus 1 I j minus 1 minus p dash I j. These four equations will come in picture now. Let us write our continuity equation in the, you can say, incompressible field I am writing, and here you can write it by this du by dx dv by dy is equal to 0, or I am calling it as dij. Okay, something I am calling this as dij, yeah, which is 0, equal to 0. So let us discretize it. So after discretizing, what will we get? This u dot del is equal to, so this uij minus uij at previous point. So we, after applying the backward difference method, I am writing, so uij minus ui minus 1j divided by delta x I am writing. So here I have these two values. I will apply here. So I am directly doing it, which is uij tilde plus at n plus 1 plus delta t by delta x p dash ij minus p dash I plus 1 comma j. This is the value here, and minus u tilde I minus 1 comma j at n plus 1th time step minus delta t by delta x p dash I minus 1 comma j minus p dash ij. So this term has been discretized here, divided by this is delta x, so delta x. So discretization of this term, plus similarly for v tilde ij at n plus 1 plus delta t by delta x p dash I j minus p dash I j plus 1 minus v tilde I j minus 1 n plus 1 plus minus delta t by delta x p dash I j minus 1 minus p dash I j. Yeah. Yeah, you are correct. Yeah, correct. It is fine. Yeah. So till this you understood. So this whole thing will become equal to 0. Okay. So let's add these terms. This minus this minus this divided by delta x divided by delta y. So what will it become? So let us write it. U tilde I j n plus 1 minus u tilde I minus 1 comma j n plus 1 divided by delta x plus v tilde n plus 1 minus v tilde I j minus 1 at n plus 1 divided by delta y plus all the terms. So I am calling right now as residual, but later I will write it. So this is actually dij. So del u tilde by del x plus del v tilde by del y. So this is like that, but this is not equal to 0, which I am calling it d tilde ij right now, plus delta t by delta x square, because this delta x will go and this delta x, this will become delta x square. And now we will write the pressure term p dash I plus 1 minus p dash I plus 1 comma j. Just a second. Yeah. P dash I plus 1 comma j. This minus p dash I minus 1 comma j plus p dash ij plus delta t by delta y square, and then 2p dash ij. Here also it will become 2p dash ij minus p dash I j plus 1 minus p dash I j minus 1. I hope you get it what I am going to do next. This is the equation of central difference. So let's write it. Central difference, why I am calling it as central difference. So next, d tilde ij plus, or you can say minus delta t p dash I plus 1 comma j minus 2p ij dash plus pi minus 1 comma j divided by delta x square minus, this will also become minus, and p dash I j plus 1 minus 2p dash I j plus p dash I j minus 1 divided by delta y square, which is equal to 0. So it will become like dij tilde minus delta t del square p over del x square. So I'm reconstructing from discretization to reconstruction. So del square p over del y square equal to 0. So this reconstruction, I hope you got it. So this will become yeah, fine. So it is just for, it is fine. Okay, so del square p This will come at the end. Mm, Actually, p dash should become 0. Our objective is to make p dash as 0. Like automatically dij will become 0. Dij should be 0 actually. Dij tilde is not 0 because it is coming from predicted pressure values. Dij is actually continuity equation, so it should be 0. Hope you got it. So this p dash. So one more thing, p dash ij. One second. So now I'm writing the algorithm. This much you understood. And now if the pressure values for the neighboring points, if they become 0, these points, if they become equal, then we will be left with pij only, p dash ij, or you can say. So this p dash ij, if we want to calculate from this equation, so this you will get it later, but I am writing right now. P dash ij will become minus d tilde ij. So this will come in algorithm. So 2 delta t, yeah, 2 delta t, because we will add these two, and 1 by delta x square plus 1 by delta y square. For this you have to be patient. So bit patience. So I am writing the algorithm first. I have written it. So what you have to do for my algorithm. I told you to be bit patient. I'll write it. How we will get it, I will tell you. First, for this algorithm, what we have to do is set our grid and boundary condition. Then calculate delta t. So in this we will calculate using our one thing is necessary condition, which is CFL condition, or von Neumann criteria. So in this, I want to ask one thing, that sir told you in this way or some other way he taught in the class? Totally different way. But it is a... Huh? Yeah, we can neglect it. Yeah. That is why, yeah. This is how it is done. So simple algorithm is bit more iterative than this, and the results are more accurate in that. At t is equal to 0, we have to initialize the problem as we do in CFT, and then calculate this u n plus 1 v dash v tilde n plus 1 by Navier-Stokes equation, because we predicted pressure and velocity at the initial values. So we are writing this, and then fifth, calculate d tilde n plus 1. We have to calculate. Sixth point. Before sixth point, I want to write it like this. So here, if in this iterations, why I have written this, I want to be clear in this first. Then I will write the sixth point. So this in iterations, when we go for iterations, this u tilde will become u at the end, v tilde will become v, d tilde will become d, which is equal to 0, and this should be in the range of, the error should be range of 10 to the power minus 6 minimum. And for this, what we have to do, in this delta t can't be 0. Okay, so let me write it. And delta x and delta y is also not 0, then it only becomes 0 when p dash is equal to 0. And this p dash, pn, it will become 0 when pn will reach pn plus 1. So then p dash tends to 0. Okay, and then when it will happen, this pi plus 1 and pij, then pi minus 1, this pi plus 1 will become equal to pi minus 1, and pj minus 1 equal to pj plus 1. So this is how we are dropping neighboring pressures here in the spatial direction. So we are assuming the spatial direction as the constant pressure, and in time we are varying. So this, when this will become 0, we can neglect these terms here. Okay, so this was just for final review, but here if we can drop these terms here, then it will become 4 pij, something like that, and then this will come into picture. Then p dash ij only will be left, and asking something? But yeah. Actually, we have to reach there for, like, in the, when you apply the algorithm. So this is for calculating the d tilde ij for one time step. When you apply the algorithm, the pressure will not be the same everywhere. So it is for one time step only. When you apply the algorithm, so this is for one time step assumption to calculate at least. Yeah, at least starting the algorithm to calculate it. So we will calculate, how will we calculate the d tilde ij? There is no way of calculating. Yeah, this is the assumption actually. So this p tilde ij, when you calculate from this, we will find the p ij n plus 1, and we will put this as pn for this time step pn ij in the Navier-Stokes equation, and then again find the u tilde and v tilde, and again and again this procedure will go on, and we will get the p dash ij as 0. Yeah, you will get it. you will get it. So it is, I tried to make it as simple as possible, but it is bit tricky here. This point is bit tricky. Check. Yeah, you can do it. Yeah. So I reached till this t tilde n plus 1. We will calculate this and check. So this, how will you calculate? You know the u tilde, v tilde value, and you will calculate the t tilde n plus 1 value. Then we will check this t tilde is less than error or not. If not, then we will do something. Then we will see that if it is a steady state or not. So I will write later. But at 6 point, I will again come at 6 point. Let's come to the 7th point. We have to calculate here. After dropping the pressure terms nearby, I am calculating that P dash Ij as minus T tilde Ij. So I know the T tilde here. If it is not, then I am moving to this point. So just think about the algorithm. First we set the grid and boundary condition, then calculated delta T, initialized with some pressure and velocity, then calculated from that pressure we calculated and velocity, we calculated the u tilde and v tilde, and from this u tilde v tilde we calculated d tilde value at n plus 1 next time steps, and we check at every time step. We have to check that it is converged or not. So obviously in the first time step it is not converged. So we will come to the next point, which is 7th step of this, is which is 1 by delta x square plus 1 by delta y square. So this is just for calculation of this p tilde ij term if it is not satisfying. So this we have to update now. Update our pressure. We have to update our pressure with Pij is equal to Pij plus P dash Ij. So whatever P dash Ij is there, we will add into the pressure here, and the total pressure will go for the next step. And then we will update velocity now. So you have to think into the for loop sense or in a iterative sense. At every time step some improvement is going on. So u and v we will calculate, and then 10th we will apply boundary condition. So I will write something here. When you will think again and again in the iterative sense, then you will understand what I am trying to, if you are not getting properly. Near to. So, but this is the very basic sense which I am illustrating. You can think of Mach algorithm in a different sense also. Then boundary conditions. And after applying this, we will go to 5. Okay, again 5. This calculation of t tilde n. After updating the velocity, we again calculate the t tilde nj, and this. So this is kind of a basic algorithm term I should write, but from this we have to go to 5. After applying this, we have updated the velocities here, then apply here. dt dash, we will again check if it is less than this, and again calculate the p tilde, again update it, and at the end, if this happens, then we will directly go for step 11, which is what? Check for steady state. Because this t tilde will become less than error, which becomes equal to 0, and pressure is correct for the next time step, Then we will check for steady state, which is another step just. So un plus 1 is should we become equal to un plus 1 and un, and vn plus 1 should become vn, which is the condition for steady state, that all the velocity will become equal with time. With time it is not changing. That is why we are checking for a steady state. And then 12 means for 1 to second time step, and then t will become t plus delta t for the next time step, and go to 4 again, step 4. So for the next time step when we move, for the next time step when we move, for this time step we have calculated, and we have said that it is reached a steady state and our values are correct, and we have calculated the pressure values, and then we will again add the delta t in the time, and again go for that iteration for the next time step. And now you can ask questions. You should get the crux at least. Later you can learn it from any book, but this is the crux. This is how we go for Mac algorithm solution. Sorry, derivation. Yeah, exactly. So let me go for last time's code first. So this I am stopping. Last time we were doing some code, so I will complete it. Which equation? Right now? I'll share again. Yeah. What do you want to know about this? I'm asking, Mapper, what do you want to know? So this is not exact correct equation what I am writing. This is for the prediction what we have to write. It is when you neglect the neighboring point. So maybe I think it is not bit clear to you. I'll have to take it in a separate thing, like yeah, that I will upload, but yeah, I should be able to actually Okay, I'll explain it to you later. Right now also I don't have book right with me. So later I will do it. This part you just keep in your mind. Okay. It is actually from my notes. Yeah. I don't know which book. But it is a reliable source. That I am not saying that it's not a reliable. It's from my professor's notes. I don't know. Yeah. I'll look for it. I think it is from this Malakkar's book. Some Malakkars is there. I'll tell you. Malakkar. Malashekara. Versteeg and. No, no. No. It is a Melcal. It is Mac algorithm. Piezo is very different. Piezo is for like it's a higher. You can say when you go higher in the simple algorithm or pimple algorithm, then you will get piezo. So there you will get to know about some more iterations. Here it is the least iterations applied. These all are similar, but in uh, in that simple algorithm you will directly predict the pressure. This P dash will be predicted, and from that V star or P star will be predicted, and then you will go for the next steps predictions. Here it is not like that. Here you are predicting velocities and minimizing the velocity by continuity equation. So this is for that is why it is called as from here. They are also in simple algorithm you will get to know about the staggered grid applications. So there the velocities when we predict or when we apply the velocity, it is by the staggered grid. You can watch any lecture, I think, by Suman Chakravarti sir. That lecture is more than sufficient for simple algorithm. I don't know. Yeah, so it is not clear to you, simple algorithm. It is. Yeah. Yeah, so this is Mac algorithm which I discussed. I am very sure. Yeah, I am very sure. You can. This is Mac algorithm. This is how it is done. The algorithm I wanted to write, that algorithm. I am not taking any code about it, but yeah, this is the Mac algorithm which I took. According to you, which is the Mac algorithm? And this is not pimple actually or piezo. Those are completely different. No. The piezo and pimple are the, you can say, advanced version of simple algorithm. Simple revised, yeah. In simple revised, some more implications are there. So, and in piezo you split the operators. Okay. So this much I can tell you. You can say here. I am not sharing the screen. I think here this I have written. Okay. I should share the screen then. I don't know which term, that Dij term is not clear to you. That I understood. But for one time step, we can assume that in spatial direction there is no so you are not understanding the difference in those two time steps. One is the time step which we are varying. So for the next time we want to know. But for this algorithm, we are having different, like from I is equal to 1 to suppose 100 we are moving. So for one iteration we are assuming that Pij I minus 1 is equal to Pij I plus 1. The Dij equation which you were asking, it is for one iteration. For one iteration we are assuming. Hmm. Mm-hmm. Hmm. No, so PD I just showed you that it will be converted like that. But at the end I discretize it. After discretizing I make it 0. When I upload, you again watch that video, okay? And if you have doubt, you just mail me. You know my mail ID. You know my email ID. Okay. Okay. So for the last time's problem, I am writing just the code I am writing. So it was for staggered grid, which we were about to solve by the artificial compressibility method, which I told, and which all of you said that it is pretty clear to all of you. So I was about to write the code. I am giving it. Maybe it is useful for your assignments. If you forget, was the week 8 lecture. There I covered, and week 9's I think some part I covered this. I forgot in which I covered. So I am assuming 51 points. These are the terms which are completely same as previous codes. So I am not changing anything. That is artificial compressibility. Later it will become 0 when this dp by dt. So for pressure prediction, that some term so in this code also it will be clear. So that del is artificial compressibility. Oh, that will not become 0. That is why the dp by dt, when it reach the steady state, then only the total will become 0. The total term will become 0. Artificial compressibility, we will give some method or some value. Right now I will give. So this something is there, 1 by 4. Suppose 1 by 4 and dp by dt is 0 there. Okay, I predicted that del value is 4. Okay, then what will happen? Then dp by dt will become 0. This whole term will go to 0. So this artificial compressibility method is for steady state solutions. So when we reach the steady state, this dp by dt will automatically become 0. du by dt will become 0. duv by dt will become 0. The total will become 0. So this unsteady terms will become 0. Then automatically that term will go. Okay. These are same. Then I am discretizing x from 0 to domain length in h sections, in different section by h difference. Okay. Similarly, I will do for h. So these are the same steps as previous codes for 2D code. Uh, then now we'll predict the, or you can say some starting values of dt, okay, which is for time advancement. So these doubts will be clear when we write code. For Reynolds number also we have to predict, because in that momentum equation we have this Reynolds number 1 by RE miscustom. So yeah, for that I am writing. So that delta is this. I am predicting, suppose this 4.5 as artificial compressibility. Now we will write it in equation. We will initiate. Yeah. Collocated grid. Hope you got and remember. So these are the collocated variables, which is for that staggered grid. So till this, let's take some 10 minutes break and 5 minutes break. Okay, 5 minutes break. Then I will again start, because it has become 1 hour. So others also can take. So I am back. Let's start it again. So this finite we were here, finite collocated variable. So u at and so this is the u matrix. So which is n underscore points is equal to 0. So this is from that collocated grid. So hope you remember that. And if you don't remember, go back and watch lecture number 9. Sorry, 8. For week 8, I think. So we in this endpoints plus 1. P is both the endpoints will become plus. Then u final is 1 comma all the columns will become 1. We are writing it as 1. And then let's write about the staggered variables. 1 u. So we have two variables here, one is normal, one is staggered. Similar way, we'll go further, which is also is equal to 0 in the starting, and similarly P pressure, which is staggered pressure. So I have not written. Okay, I think I have put something wrong here. Yeah, this is u final, not u. The code here, final. V as V final. So finally means whatever we are getting, and P as P final. So I have written for U. For first row, all the columns I am writing the values as 1, but for other values as 0. And for P, for total endpoints plus n plus 1 plus 1, all the things as 1. But for staggered variable, I am writing in a similar way, but we have to start it with something. So similarly, it's a starting values. Yeah, you can say that. So as I said, okay, so let me write the code, then you will understand, because at each points I can explain the previous things, because we lost the previous algorithm now. In my mind it is there, but I think you guys forgot it. So let me write it, so that this time also it will not be left like other times. 2 weeks from last 2 weeks I am missing it. I will explain it. Let me complete. I didn't miss any point. These are stubborn. Now will come for solving. So these are the point as previous codes which I already explained in like 4 or 5 times. So why I am these are new points which you will get later in this algorithm. So these things I have explained in theoretical way, but not in this sense. So yeah, you will get it. Error. So let's start a figure 1 for error monitoring. So I'll also make the error monitor here in the figure. Okay, so that plot I will make. Here pressure term is coming. Okay, now this is bit new as compared to previous code. So this for j plus 1, that is standard pressure minus P at ij diffusion term. Let's do about the diffusion. So as I explained in the theory, these terms as this PG term, pressure gradient term, then diffusion term, then convection term. These three, advection term, or you can say. So these three terms I explained in I discretized it in a 1 by 1 manner. Right now you can go to the previous lecture and see how I did it, because it will take another hour to again explain that. Code is bit huge, so I want to complete it. So what one can do is just see the code and then try to understand the algorithm. I will upload this code so you don't have to write it, but you should practice by your. this is center difference. For the y10, this is bit large, so yeah, one can see diffusion term. The right hand side term is d square u over del x square plus d square u over del y square. That is what I have written here. 1 by r is there outside in that is non-dimensionalized form. So this is the central difference of del square u over, this should be v, I think. Yes, this is u, this is u, this is u, this is u, del square u. Which thing? H square. Yeah, for the, like, this can be taken, you are correct, but I want to show this is the center, another one center difference, and this is one other center difference in the, this is actually del y square and this is del x square, because we are assuming del x is equal to del y. That is why I am writing in this way. Okay, both will be same, but I want to represent it in a proper way. So advection in let's write advection in x direction, means the left hand side term in x direction, which is 0.5, 1 by 2. Why I am writing 1 by 2 is this yeah, that staggering I did, that staggering is uij plus ui minus 1j by 2, something like that, means ue is equal to ue plus up by 2. So that is what I am writing here. So I want to again say that if you want to understand this code properly, you have to watch the lecture or my session which I do, because it's a big code, I can't again and again do it. I ui plus uij plus 1 means u at present point plus u at northern point, or yeah, northern point by 2 for u at small n. For staggering I am writing it, and then 3 square also I have to put. So del u square by del x, so plus okay, this should be here. Let me check it. Square minus 0.5 into similar, but here uv will come, so u 9 comma j plus u 9j minus 1 2 3 square, then I will close it. And then advection in y. Just go and watch the advection discretization in my picture, then you will understand. This is the reason I want to complete it that day. Getting a bit complicated, but you have to do it. This is UV term. I think I will make some mistake in parenthesis. The most complicated part is over. For u nu ij is equal to u I comma j plus that diffusion. So this is the u discretization divided by delta t, u at next point plus u previous point divided by delta t. So this delta t is coming here as I explained in the lecture. dt is coming here, and I am writing diffusion term, diffusion minus advection. So this advection will go to next side, advection in next direction, minus advection similarly in y, or plus pressure. These terms already defined here, and then we will write end of this for loop, end of this for loop. So this is for all the things are defined for this calculation, new values of new calculation, and let me see, it is a big code actually. Me too. the whole Navier-Stokes solution, so it will take some time to grasp also and to write also. It is a big code which I am giving it to all of you. This one can use in solving the assignments also. So it will take a lot of time. I think it is a bit boring process. Apur, Gopinathan, Apur. Yeah, I want to ask that should I just upload that code better than writing it here? It's a bit tedious process, and as compared to that, it is a bit boring. Yeah, I can explain it. For explaining also, I have to write. So better to upload it and then ask question next week. According to me. Because I'll upload and it's a big code. Later you will ask a lot of question in this. You can ask. First you have to look for that lecture and yeah, that is fine. That will be fine. So I'm just copying it in this year's this week's notes. This code I'm copying. MATLAB code. So other things you can also tell me that if you are facing any problem. Next week should I cover? What should I cover? Okay, directly I will copy it instead of writing. You are correct. Yeah. That I know. Yeah, you are correct. I am copying the code right now so that I will not forget it and upload it and show it to you. In notes I am copying it somehow. Next page. So I have uploaded this in the folder. Can you check that you got it, the code? In 10th week's notes also I do. Yeah, that Google Drive link in which my notes I upload. And same thing. There will be a SPI file. That SPI file is for this code, and in this 10th week PDF also I copied it. So can you check that SPI thing? You can just go and copy paste that SPI for your code just now and check your code is running or not. Week 10 is also uploaded, but SPI thing is also there, SPI PDF. Just look for SPI. In that, I think I have uploaded. I uploaded it. Where I upload my notes, that drive. There is one SPI.pdf named folder. I'll show. How can you not find it? This SPI folder. Can you see my screen? This is shared by everyone in the lecture things. So here if you go, this CFD notes. So there is a problem solving session. Here this problem solving session is there. You click here to view. So you guys don't even know about this notes section. So here I uploaded. So this is for previous, okay. Yeah, here my notes are uploaded. So can you see right now? Just got it? That SPI thing. You copy it and then let me know that if you can run the code. So this is the code from here also. If somebody not get it, you can copy. This is for Navier-Stokes equation solution, and in my notes of 10th week I have explained the MAC algorithm first, and later I copy pasted it. So you can see this copy pasted code, which is for full Navier-Stokes solution by artificial compressibility method. Okay. It's okay. Now I think we should conclude this meeting, and next week, as you said, that I will explain the simple algorithm, and what I will do is similarly I will cover a code by simple algorithm for lid-driven cavity. This is also for lid-driven cavity problem. So with simple algorithm we can do it. So for that I will cover next week, and next week I will cover turbulence problem, and then Malashekara. Okay, I'll supply the that book in which I will get the MAC algorithm here. In this folder I supply notes. So you see this week 3 lecture notes, everything is there, and steady diffusion equation, other codes, everything is there. Yeah, this somebody asked me about physics of fluid paper, that also I've uploaded. Everything here is uploaded. Okay. Yeah, I think somebody asked me. Okay. Okay then. Take care.